Hello. Not seeing anyone who has joined in, so let's wait. Hi, Rohi.
Hello.
Okay, maybe we can give it a start. Let the others join in. Yeah. Give me 1 minute. I'll share my screen.
Okay.
Okay. Yeah. I hope you can see my screen now.
Yes.
Okay. So yesterday we closed with the multiplication rule, and we looked into the case where events are not independent, and we took an example of two cards which are drawn in succession after one another. In which case, after every draw, the only condition is after every draw, the selected card is not replaced. And then we tried to find out what is the probability that in both the draws I will be getting a spade. Okay, so that's uh, just a moment. Yeah, so that was the example which we took, and we saw that if, let's say, A is the event of getting a spade in the first draw, so A is getting a spade. I think we have written it where? Yeah, here. Yes. So A is the event of getting a spade in the first draw. So there are 13 spades and 52 cards in the pack, hence then it will be 13 by 52. Now we've already drawn a spade. So let's say we've got a spade. Then we have one less spade and one less card. So then the probability of getting now a king of spade, right? So and then again to get a spade maybe, is going to be 12 by 51. So if I want to take is kind of a probability calculation where I'm talking about independent or not independent events in this case, I'm sorry. Then in that case, I simply multiply the two probabilities. Now here I see something which is happening over here, and that is going to cause or raise us into the next set of problem statement that we have. So because we are decreasing, and the reason why we are decreasing, maybe the statement was wrong. So the reason why we are decreasing the count is because there is already a condition which is already getting implied on the first step. So the condition which is getting implied is condition we are not putting the card back. Okay, so we are not putting the first card back. So in the second case, the sample size changes, and it also depends on whether I've properly done the experiment at the first go and that I've not put back the card. So that condition has to be met. So this is a case where this is obviously a situation with not independent events, but this is also a case where we can talk about uh, conditional probability, and that's the next step that we are going to take. But quickly we need to look into other areas first, and then we can go into conditional probability, because conditional probability is going to be difficult to understand right now. We need to understand probability distributions and something known as Bayes rule. So before we understand Bayes theorem, let's look into another kind of probability, and then maybe we can get back. But just to give you some intuition, I'll try to write what I'm trying to say over here. So we are trying to find the probability of some event A over here, which is getting intersected with another event B, right? So we are trying to do the same thing over here. It is an intersection, and the intersection is represented by this term. Now, when we are trying to do this, what we do essentially is that we simply take the probability of A and then the probability of B, and then we do multiplication. That's all we do, right? But in this case, what I see is this probability B, or this event B itself, is dependent on a condition that I've applied on the event A. When I was doing the event A, I have taken a condition that we are not putting the card back. So this is the condition. This condition satisfied, then only this number makes sense, or otherwise this number is not going to make sense, right? This number will again be 13 by 52 if I put the card back. So in this case, a better way of representing this is, I'm not going to say I'm going to multiply probability of A into probability of B. Rather, I'm going to say I multiply the probability of A with the probability of B, obviously the probability of B, given I have done the activity which was there in A. So given I have an event A, which I have already done, so I have already picked up a card which is spade, or I have already got a card which is a spade. Then what is the probability of getting another card which is also spade without keeping the first card back? So this is a very common representation of conditional probability, where one event is dependent on the other. So this is the independent event. Okay, so this one I can say this is the independent event. Okay, and on this independent event I have an event which is dependent, which is this one. So this is a dependent event. So B is somehow, there can be many forms of this kind of, let's say, dependency, and that is going to determine how we are going to conceive the formula, or how we are going to conceive the calculations. So there can be multiple ways of, let's say, dependencies. Okay, so there can be multiple ways of, let's say, dependencies, basis which we are going to decide what is going to be the formulation. But this is just one way in which we can decide, right? So from here we can find out something very interesting as well, which we'll look into later on, but it's a good time to give you a quick intuition, is that probability of any event B where I have a dependency. Hi Rohi. There was a small problem with my internet connection, hence it got disconnected. I don't know whether that first part, I'm sure
Oh,
that first part will be recorded. So let me just reshare my screen. There's a lot of rain going on in our area, so the electricity is going on and off. That's why we are getting the disconnections. Okay, so what I was
no
saying is,
issues, no issues.
I have a probability. I need to find out the probability of A intersection B. Okay, and A intersection B is, now I'm trying to define it as probability of happening of an event A multiplied by, so this is the multiplication sign, probability of any event B. In this case, any event B is now a dependence on A. So A has to happen and then only B can happen. Now, there is something which A is doing basis which B is happening. Now, a very quick mathematical derivation from this formula or from this line is something like this. So probability of B given I have A can also be represented in the form of probability of A intersection B, of A and B are the two events which may happen uh, as part of the experiment that we are trying to do, where we are trying to apply the multiplication rule earlier, right? So we tried to apply the multiplication rule and we got this, and now I can divide this with the probability of A, right? So if I divide the probability of A integration B or A intersection B divided by the probability of A, I get the probability of the dependency, or how much is the probability dependent for the event B to occur if A has occurred. So this is something we will look into in great depth into later on. As of now, I don't want to go in there because I need to cover a couple of things first, then only we should go there. So I hope until this point in time it is clear. Let's go ahead and look into something else. So I'll quickly explain one more type of probability which we have, and then we will look into something else. So these are rules of probability, types of events we have already seen. We have seen types of probability. Now we are going to see a very special kind of probability. Okay, this special kind of probability is otherwise known as marginal probability. Okay, now let's define marginal probability properly first. If I'm not able to define this, we won't be able to understand. Marginal probability is simply a very well-known technique. It is just a technique. Okay, so you can consider that as a technique. There can be multitude of definitions in variety of books, but I would like to call that as a technique. A technique by means of which I can find out the occurrence of some event, provided something has happened or not happened. Okay, so there can be dependence, there cannot be dependence. There may be dependence, there may not be dependence. But I just want to find out the probability of some event happening because of some or a set of experiments. Now, I know that when we are doing this activity or when we are trying to figure out this kind of probability, we have already seen a lot of formulas, we have done a lot of calculations. So for each and everything, we have a formula. We can simply write that down, create a cheat sheet, and whenever we need to apply some kind of a methodology, as we saw in this example, for example, we saw in these two examples, we looked into the problem in great depth and we figured out what that problem essentially means, and then we applied a formula. The moment we solved the formula, we got the probability. This is the simplest way. But this is a mathematics way, or this is a mathematician's way, because every time you need to apply some kind of formula and you need to have this kind of a knowledge in the background as well. What marginal probability is saying is, let's say I am in a certain situation, and for which I'm going to take an example as well, very easy example. I've already prepared an Excel sheet with some data which I'm going to share after I explain the example. So what if I have the formula? So what I was saying is, let's say I have the formulas. With the formulae, what I can do, we can provide a mathematician's view or a statistician's view. Okay, we see the question, we understand the context, and then apply the formula, right? So this is one way of doing it. The other way, the other easy to interpret way of doing this is to create a table. Okay, now what do you mean by table? The table is as simple as, if you have worked with the databases, then you know what is a table, right? So you have rows and columns. It's a tabular representation. In Excel, any Excel sheet is going to be looking like a table. It's going to have columns, it's going to have rows. You can name them, you may not want to name them, up to you. It actually depends on your data. And then if you're looking at a very big data or a very scattered kind of a data, putting it into a table is going to make a lot more sense. We have already seen an example of this earlier, if you remember. When we did not look into probability, we were looking into univariate analysis and probability density function. We created the frequency table, and then we also created the grouping of data, right? So that we can create the histogram. So that tabular representation was very easy or very intuitive for us. When we actually arrived at that, it was really very good for us that we could arrive at that kind of a table, and that we could let's say summarize. And looking at the summarization, we were able to answer a lot of questions. So that is the basic of marginal probability. Then why is the name marginal? Marginal because I know the answer already to some extent. Okay, so that is the situation here. Marginal probability, or this table which I'm going to define, this table has a name actually. So we have a name of this table, we have a way to create this table. The table will be created out of the question itself that I am asking. So basis the question which is being asked, basis the business problem, I may want to create a table which is in turn going to have some data, but it's not going to have the other set of data. So imagine you can try to visualize a table in front of you, which has, let's say, 10 rows and 10 columns, and you have data only into 3 rows and 3 columns. The rest 7 rows and 7 columns are empty. Now, some of the cells have data, some of the cells don't have data. In this case, I just have to reverse engineer and try to fill the rest of the cells if I possibly can. Okay, there is a condition behind this. At least some of the tally has to be matching. We will see that when we look into the Excel sheet. But some of the conditions, some of the prerequisites has to match. If that's the case, then we will be able to easily recreate that table which has the missing data. So we can impute, we can try to calculate the missing data. I'm not saying that I'm going to put any value. I'm actually going to logically or mathematically calculate the values in the fields which are missing in that table, right? So if I can do that, then what I can do is that I can create a table, and this table is otherwise known as a contingency table. Okay, this contingency table is represented by means of marginal probability number or marginal probability value, which we are going to look at. Okay, don't worry. Now, if I'm able to create such kind of a summary table, a summarized table, then it becomes very easy for me to answer probabilistic questions as well. So that's the example that we are going to see. So we are going to take an example, and then we can see how this marginal probability thing works. But as we see, the term marginal is used to integrate or indicate that the probabilities are calculated using a contingency table. And that table is also known as, there is one more name that you may find. So I'll just write this over here, is also known as, okay, joint probability table. Why is this so? We are going to take an example, then we can see. Okay, it is also known as a joint probability table. And in that table, some of the probabilities are already there, or some of the happenings are already recorded in terms of probability or in terms of percentages. If you do remember, we took an example earlier where we figured out the probability of some dice example or some card example. Yeah, here it is. Right. So this was my favorable outcome. This was the sample space. So I figured out the probability, then I could represent that as a percentage. So either the question will be posed in terms of a probabilistic number, which will be a fraction between 0 and 1. We know that already, 0 and 1 being the extremes. Or it will be presented in form of the percentages, which we can easily backtrace into a probability number, right? If that is going to be the case, then I can clearly find out the rest of the missing values, which we are going to do now in the exercise or example. And then we can also find out the answer to the questions which I want to answer. Okay, so let's go to that example and let's see how we can do that. Okay, a contingency table, just to give you an overview, by definition, it consists of rows and columns of two attributes at two different levels. And the values or the cells in that table will be filled with frequencies of each and every experiment that we are doing. Right, so it's going to be like a matrix. Okay, and that matrix is going to have some numbers basis how we are going to fill up the number. Okay, so let's take an example and let's try to share an Excel sheet which I have. I'm not able to find my Excel sheet. 1 minute. New share, show all windows. Where is my Excel sheet? Where is my Excel sheet? Yes, here it is. Okay. I hope you can see my Excel sheet here. Yes. Okay.
Yes, yes.
So this is the question. This is the scenario. This is the question. Okay. So this is the question. So I'm going to highlight it as yellow. So this is the scenario. I have a used car lot. Okay. There are a lot of, let's say, vendors like, let's say, Mahindra and so on, who have used car companies, right? So they buy used cars. So customers can go to them and sell their used cars, and then they refurbish those cars to a certain extent, and they are going to resell it back to customers. The people who are interested to buy used cars can go to those shops and they can buy. Now, imagine any company ABCD or PQR who has a lot of cars in their used car lot, and in there they are seeing that 70% have AC and 40% have a CD player. They also find, okay, Saransh is trying to join, let me add this. So they also see that in these cars, 20% of the cars have both AC as well as the CD player. Okay, maybe CD player is sounding a bit old age, but it is the situation. So you have 70% of cars with ACs, 40% of car with CD player, and 20% of car which has both. I want to find out what is the probability that a car has a CD player given that it has AC. So I'm trying to find out a conditional probability here, right? So this question is clearly giving you an idea or an intuition as to what marginal probability or what this process of calculating marginal probability is going to talk about. It talks about something which may happen or which I want to find the probability of that happening basis something else has already happened. This is what we looked into when we saw the cards example, right? I drew a card, I did not put it back. And keeping that as a condition, I want to draw another card and see if it is still a spade. So that is the reason why we did a 12 by 51 rather than a 13 by 52. Had it been the case, I had put back the card, it would be 13 by 52 probability for event A as well as 13 by 52 probability for event B as well, right? So that's the point. Now, my question here is, give me a moment. So just a moment, I'm getting a call. Okay. Okay. So in this example, what we are going to do now is that we are going to look into this example that we have already taken up. And in this example, what we have to find out is a conditional probability kind of a thing. Okay. So how we are going to find that? Let's first of all look into how I have filled up the numbers. And then let's look into what is this marginal total thing. And then we can look into how to do the rest of the activity. The moment we complete this table, this is the contingency table. The moment we complete this table, our job is done. We will be able to find out the answer that we are actually looking for. So let's say I'll just insert one row over here and I'll do a formatting. And then I'm going to say wrap text merge center. And then this is my contingency table. Okay. So I'm going to do, let's say this color and bold. Okay, so this is my contingency table. The one that follows after this line is going to be my contingency table where I have some attributes. These attributes in italics have come from the question that I have. So in the question itself, I see cars with CD as well as no CD. I have cars with AC as well as no AC. If I take a combination of this, what kind of data do I have and how did I find out all these numbers? Let's try to have. So if I try to have a look, I can see that there is a clear case where people are saying 20% of the cars have both. So cars having both AC and CD, intersection of these two cells is 20. Okay. Then the question, the problem statement says 70% have air conditioning. It does not talk about whether those 70, how much of that 70% has a CD player or no. So I put that over here. This is called marginal total. Why this is a marginal total? I don't know the clarity. I don't yet know the clarity as to out of that 70%, how much has CD, how much has not got the CD, and so on. So that is the reason why this column is called marginal total. Okay, because I know something about this total, but not everything. And then I have another number which says 40% have a CD player. So 40% have a CD player can come over here. Now, how I have calculated these things is that, let me just delete this. So these three numbers are provided by the question. If I try to tally this table, the first rule of creating this table is that sum total of marginal should be equal to 100%, because if I'm taking a percentage, nothing can be more than 100, because we are talking about the probability game here. Okay, we are talking about the probability game. If we are going to talk about probability, then the range of probability falls between 0 and 1, which converted to percentage is 0% to 100%. Either we say there is a 0% chance or a 100% chance. So this should sum up to 100. This should also sum up to 100. So I will write 100 over. If this is equal to 100, how much is this cell? Obviously, this will be 30. Right? If I have the first cell as, let's say, 70, then the second cell has to be 30, or otherwise it can't be 100. Then again, in this row, I have to put this as equal to 60, because if this is 40 and this is 100, then what is left over is obviously 60. So at least some part of my table is now complete. At least I am able to complete the marginal total. Now let's try to complete the rest of the cells. So step 1, I take this value. Step 2, I complete the marginal total. Step 3, I try to complete the rest of the cells. Okay. What can be this cell? This cell will be equal to 50. Why will this cell be equal to 50? Because 20 plus 50 has to be equal to 70. So I have to match the equation, right? So it is like 20 plus, if this is an unknown, so 20 plus x is equal to 70, then x becomes 50, right? Then I have two unknowns here. How do I calculate that? Easy. I have yet again two sets of equations here. 20 plus x is equal to 40. Then what is this 20? 50 plus x is equal to 60. Then what is this 10? You see the numbers also match over here. Right, so the totals are going to match. If you take a total like this, it's going to match. If you take a total like this, it's going to match. Right, now that I have created the contingency table, first step was the sum total. I took 100% just as a sample value, because I have to total it to 100%, right? So that's how I do it. Then I have put the initial values I got, which was 40, 20 and 70. These three were provided already to me. Let me put them into some other color. The first step is this. I did this. Then I filled up these two cells. Okay, because I had to tally these cells. I have to complete the sum, and then I filled up the rest of the empty cells, right? Once that is done, I can now try and answer what is the probability that a car has CD provided it has AC. So this is the line I should be interested into, right? I should be interested into this line, but here comes the trick. The trick here is, if I'm using a contingency table, I need to use the marginal total and not the individual total. So what I mean by that is, the car having, or the percentage, or the probability of a car having CD given it has AC is 20 divided by 70, right? Because the total number of AC is equal to 70 and the CD occurrences is equal to 20, right? Now this is the general way of trying to find it out. How did I do that? Because I have simply calculated that. Maybe this was a very simple question where I already had the values of 20 and 70 and 40, and hence I could simply divide 20 by 70. I would have got the results. So there was practically no need here to fill up the rest of the cells, because 20, 70 and 40 were already given to me. But creating this table is going to solve a lot other problems. So my problem statement of P, or probability of CD given AC, is solved by this 20 divided by 70. So this is the probability. The probability is, if I just take this cell, let me just take this cell and try to do this. So I'm going to multiply this by 100 and I get that there is a 28.57% probability that a car has a CD player provided it has AC, right? So And there are other questions which we can try and answer from the same table as well. Example given, how many cars, let's say, I can ask a question like probability of no AC in a car given I have no CD player. How do I answer this problem? No AC given no CD. Okay, no CD total is what, 60. Okay, so the denominator is going to be 60. The numerator is going to be no AC. What is no AC? This one. Right, so this is how I'm going to calculate this. So I will only concentrate on this, and I can simply find out what is the probability that given the car has no CD player, it will also have no AC, which is 10 divided by 60. Right, so this is how a contingency table is going to help. Now let's look at some practical example. Why do we at all need marginal probability concept? We are already learning so much here. And why do we need a contingency table? The reason why we need that is because this forms the basis of something which we are going to do at a later stage, otherwise known as association rules. And association rules is simply a mathematical extension. Give me 1 minute. I think I am actually getting a call. I need to take this up. Okay. Yeah. So what I was saying is related to this contingency table. What we are going to look for at later stage is a technique known as association rule mining. And association rule mining is something which is very widely used in the retail industry, sometimes in other industries as well. It has no limitation of use cases, but it is not exactly what we have done over here. It is an extension of what we have done over here. So it will not be exactly what we have calculated here. There will be other concepts like lift and confidence and things. But association rule mining is something like, let's say you go to the supermarket and you go to a section in the supermarket where you are seeing diapers for a baby. Okay, you see certain products which are kept nearby to that section. Okay, it may or may not be really related to the diapers of a baby. Okay, but they are still kept there. It is not like you have to go to a specific baby section and then beside the diaper you will find the things which are closely related to diaper as well. Things which are kept near to that set of diapers are going to be more strategically positioned because basis the association rules that the store has already calculated, they have found out a good amount of probability that if you buy this product A, then there is a very high chance you will buy the product B. So that is the essence of creating a contingency table to try and understand the probabilistic situation and try to answer questions which are basis conditional probability, because the use cases will be to clearly define the association of one event happening when something else has already happened. So let's say if I have already bought bread, what is the probability that I'm also going to buy a cheese block, right? So there must be some kind of a probability. If that probability is really high, and if I'm going to run a retail store, I will be possibly storing, or I'll at least try to possibly store bread nearby to a cheese block, because then the items getting sold together, or the probability of them being taken up together is going to increase. Hence, my sales are going to increase. Right? So that's the objective here. Clearly, it's a monetary transaction or a monetary objective that I have. Right? So that's what we are trying to do. Right?
So this is just an idea of what I wanted to share with you. I hope there are no questions. If you have any questions, please do let me know.
No questions.
No questions for me.
Oh, sorry, I was on mute. And then let's continue with what we were trying to do. So we have to look into one more kind of probability, which is an extension of the conditional probability or a very basic theorem of conditional probability known as Bayes theorem. Now we are not going to look into this right now, okay? Because if we look into this right now, there will be a problem. We won't be able to understand that because we don't know how a certain set of distributions are actually dependent on each other or how they affect each other. So maybe we take another topic now and then we are going to come back to Bayes theorem at a later stage. But that is not to say Bayes theorem is not important. It is really very, very important. We need to know that very well. Otherwise, we won't be able to do that. So we are going to do this kind of skip and hop between probability and statistics because there are a lot of terms which are intermingled with each other. If I don't understand term 1 or term A, I don't understand term B. So there must be certain kind of flow. The next thing that I'm going to look into is a probability distribution. Okay, so we have already looked into a probability density function, right? If you remember, we looked into a scenario where we took a histogram. Okay, so we created a histogram of the events that we got or the some kind of a sampling or some kind of exercise that we have got. And then what we did is that we took the output, we took the tip of each and every histogram bar, and then somehow we tried to join these tips using a continuous flow. Okay, so we are trying to join them with something like this. Okay, so if I draw this diagram now, how does it look? It looks something like this. Okay, not really a very exact kind of a representation, but it looks something like this. So with the corners smoothened out, it will look something like this. But this is known as a probability density function. This is not a distribution function. This is a density function. Okay, because this is an kind of a function or a graph which tells you that this is the area, the density is high over here. The density is somewhat high over here, but then the density is very low here. The density is very low over here. And then if I'm doing an experiment with so many outcomes, and then I'm trying to take a count, which actually gives me the height of each and every bar, which is actually the count of the occurrence of this range of events, which is signified by a bin, as we have seen earlier, then I can clearly say that there is a good amount of chance that people will fall under this kind of category many a times, because there is a good amount of chance that the density will be very high. I did a good experiment with a lot of samples, and I found out that this is where it is going to fall the most. Then it is going to be here. The rest is going to be very normal because the sides I can see they are actually declining, right? So now, how do I, or why do I need to look into a probability distribution? Now, this is a density function. This is not a distribution. So, other than probability distribution function, which is also known as PDF, okay, there is also something known as CDF. Okay, so let's try to understand what these are, and maybe we can try to clear those doubts first and clear those items first, and then we look into something else. Okay, so uh, probability functions. Okay, so here this name is not really correct. This is actually, these are data distributions which help answer probability questions. Okay, that's all. So these are a kind of distributions of the data which helps us answer the probability question. These are not really probabilistic uh, models, or these are not really the functions or the graphs that we will use to solve the actual probability function. Okay, but let's try to see what these are. So PDF or probability density function is simply created by means of touching the tips of the histogram, and it helps us understand that what is going to be the probability of some event happening, if, as we have already seen. So this gives a very rough idea of what may happen, right? The other type of density function is known as cumulative density function. Okay, this is, since this is PDF, I have to give some name to this as well. So this is called CDF. So CDF or cumulative density function gives a very rough idea of what percentage is covered by what percentage or what value. So this is a very difficult kind of an explanation that I have given. We will soon be moving over to IPython notebooks, in which case I'll take examples. But as of now, let's again go back to that diagram which we are trying to draw. So let's try to draw some diagram. We'll take a probability distribution function which may look something like this. Okay, what is really happening over here? Let's say the start was slow. Okay, it grew, it really grew, it grew fast, it went into the peak. Then it started a decline, then there was a decline, then there was a slow decline, then there was a slow decline, and then finally there is a complete kind of a decline, right? So this is the flow of the diagram. If I go from here and if I touch the tip and then I again come back and then I see over this, this is how it is going. This is a probability density function created simply out of the histogram or the representation of the histogram. What if I want to create a cumulative density function? How do I do that? Cumulative density function for this graph is going to look something like this. So this is the PDF. I'm going to draw the PDF once more. So this is PDF, and basis the PDF, what I can say, the data value started. No, sorry, undo, undo. Let me take another color because then it will be clear. Yeah. So the distribution started. It went on to peak. It went on to a peak. It went on to a peak. It went on to a peak, and then it started to slowly decline, and it declined a little bit. This is the cumulative distribution function. How is this the cumulative distribution function? Because in probability distribution in probability density function, what we are doing, we were simply looking at the frequency of each and every event which has occurred, or the bin of events. In cumulative density function, what we are doing, we are adding up. We are doing a cumulative sum of each and every value. So let's say this value is 1, this value is 2, this value is 3. So here in this graph, this is 1, then 1 plus 2, which will be 3, then 1 plus 2 plus 3, which will be 6, and so on and so forth. And I'm trying to represent a very line based or kind of a vertical graph. This is kind of a horizontal, right? So if I look into PDF was something like a very horizontal kind of a graph. Its direction was like this. But if I look into CDF is like the direction is like this. So it is kind of a vertical kind of a representation, right? How does this help? PDF helps me to identify the peaks. CDF helps me to identify something else. Example given, let's say if this y-axis, let me just extend this y-axis. Okay, so this y-axis value, let's say over here at around this tip, okay, this value over here, let's say I find out that this value is approximately 0.8. What does that mean? I tried to take a line from here and put it on this tip, and then I try to take a point down. Okay, I get a value here, right? So this is the value of x, or this is a specific value xi. So I can say this is a specific value xi, and I have a specific value over here which is 0.8, which is my yi. Okay, yi percentage of data is explained by xi values, which means if this is 0.8 and let's say this is a probability distribution or the density function of age of people or height of people, and this height, okay, this height over here is like 5 feet 9 inches, right? So this is 5 feet and 9 inches, this point that has touched over here. So xi is equal to 5.9 inches. And this is the frequency. So this is 0.8. So I convert this value into percentage. So 0.8 is a probability. It is actually a distribution, just a frequency. Converting that into a percentage is going to give me 80%. So 80% of the weights of the sample that I've taken in this example falls within 5.9, 5 feet 9 inches. It means 80% of my sample are limited to a height of 5.9 feet or 5 feet 9 inches. That is how, or that is the importance of the cumulative density function. It gives me answers to different kind of questions which are like cumulative. This is something related to the percentiles. Let's say if I'm giving CAT exam and if I have got a percentile which is 97.3, okay, 97.3 percentile means what? 97.3 percentile means what? I am better than 97.3 percentage of people who appeared for that exam, right? So similarly, in this case of a CDF, it is quite clear at this point, this tip signifying a value of this is 0.82. Okay, so it converted into percentage is 82%. 82% of the people's height that I have taken over here, my sample, is within the range of 5 feet 9 inches. So 82% of people have an average height of 5 feet 9 inches. Can I say that? From this sample, the answer is yes. Okay, so that is the use, that is the case that I'm trying to solve. Okay, so that is what I can solve from a cumulative density function as opposed to a probability density function. A probability density function will only give me some kind of a graph like this, where I can see the decline, the topmost part, I can see which falls in this range. So I can take this value, let's say this value is x1 and this value is x2. So I can say that basis my probability density function or PDF, this is the range in which maximum number of heights are going to fall. Let's say maybe this x1 is going to be 5 feet 4 inches or 5 feet 5 inches, and this is going to be, I don't know, 5 feet 8 inches. So 5 feet 6 to 5 feet 8 is what my general range of people's height is, because majority of us fall in this height. There will be extreme cases, people with 7 feet height as well, but they are very small in number. I can see over here, very small in number that happens. But in CDF, I can take kind of a percentile approach, right? I can try to categorize, or I can try to talk about the population basis if I have done a good sampling. And basis that sample, I can do a good kind of, let's say, generalization of the sample, right? So that is what I'm trying to do over here. I hope it was clear, right?
Yes, Bowman.
Okay. So let's continue with the probability distribution. We'll just go through the definition, then we can make a close, and then we will continue in the next. How do I define this? So a probability distribution, let's say now we are going to look into distributions. Okay, there are many distributions. You will hear a lot of names. So let me just quickly tell you some of the names that you will hear. You will hear names like normal distribution. This is also known as Gaussian distribution, right? So you will hear names like this, which is normal distribution. Then you have something known as binomial distribution. Okay, so these are the kind of distributions that we are going to study. Okay, but these distributions now, the ones that we are going to look into, then I have a Poisson distribution as well. Okay, so these are simply the names, or you can say the types of the distributions that I can see. Okay, the one that I'm most interested into is to bring everything down to a standard normal distribution or a Gaussian distribution. So this is, I can also say this is a standard normal distribution or a Gaussian distribution. Okay, this is also known as a Gaussian distribution, but it is a standard normal distribution. This thing has a very unique kind of a property. When we look into this, we will come to know what kind of property it is. But our ideology is to understand these distributions, how they are created, what they are, and why they are called probability distribution or probabilistic distributions. How to, if there is any way at all, to convert any distribution, let that be binomial, let that be Poisson, and there can be others as well. Okay, I've just taken a couple of examples. This doesn't mean this is not the comprehensive list of all the distribution. There are many others. Okay, it's a very vast kind of a subject. We are taking only the ones that we will need to do data analysis. We are restricting ourselves. But the ideology is to take any distribution which is not normal, and we will see why these are not normal, and try to convert them into a normal distribution. We'll do something so that they are converted into a normal distribution, because unless and until we get a normal distribution or a normal probability distribution, we won't be able to apply a theorem known as the central limit theorem. A central limit theorem is empirical to try and find out the chance of happening something. So we simply create that distribution of the probability, and then we can simply answer a lot of questions. Those questions are otherwise known as hypotheses. So let's try to understand what probability distributions are. Probability distributions, by the definition, if I go by the definition, is a total listing of various values a random variable can take along the corresponding probability of each value. Right? So what I mean by that, okay, I have a 40-minute limit. I think it's going to end soon. It's fine. We still have some time. So looking at the definition, what I mean is it is a total listing of various values a random variable can take. So a random variable is what? A variable where the value is going to change. Okay, a random variable is a variable where the value is going to change. It is our favorable outcome as well. So that is the random variable. Right? So how does the variety of values of a random variable is going to change along with the corresponding probability of each value? So let's say I have a factory, and in that factory I'm doing a distribution, or no, I'm trying to I have a manufacturing unit. I have a factory where there are a set of very important machines which are doing automated work. It is very critical for me to know how soon or how often they are going to fail. If I can know how they are going to fail, or what is the probability of them failing over a period of time or over a distributed period of time, then I can try and let's answer to questions as to how many times it's really going to fail, for how many times it will be under as a control, how much I can really control, and so on. Okay. So in this example, the random variable would be the various values the machine breakdowns could assume. Okay. So whatever the values are when the machine is going to break down is going to be my random variable. The probability corresponding to each of the value is going to be the relative frequency. Okay, it is not going to be the frequency. That is the difference between the density function and the probability distribution function. The density function is where we looked into the frequency. Right, we looked into the frequency, we looked into the histogram. Here we are not looking into the histogram, we are looking at a relative frequency. Okay, and then the probability distribution for this example is constructed by the actual breakdown pattern observed over a period of time. Okay, this is otherwise known as observed distribution as well. Okay, so probability distribution, I can try to define probability distribution. Oh, sorry, kept caps lock. Distribution over a period of time. Okay, what is the observed distribution? Maybe I'll just put this into the next one. What is the observed distribution of any event or a random variable? Okay, basis variable, basis, sorry, basis its occurrence or its probability of occurrence. Okay, so this sounds a very kind of a complex thing, but let's try to understand this by means of some example. Right, so let's take an example, but I don't think we can take an example right now. It is 2 less minutes I have. I'm really sorry for this. I think we have to close the call because it is going to close anyways within a minute. So let's continue next time. And then we are going to see some examples by means of which this will be clear. Okay, don't worry. This is the distributions that we have seen over here earlier. Okay, are basis the actual frequency. So I can say these above functions are basis actual frequencies of occurrences of events. Okay, but when it comes to the probability distribution, in this case it is above are basis relative. Okay, relative frequencies of occurrences of one or more events. Okay, this is what we are going to study. Right, I think I'll have to stop here because anyways the session is going to end. Okay, let's continue tomorrow. If you have any questions, please do let me know. Yeah. Thank you so much. Thank you for attending.
Thank you. Thank you.
Thanks
Thank
all.
you. Thank you.